So it makes sense when we're talking about concavity actually to talk about quadratics. We talked about linear functions last chapter, and then this chapter, inputs, outputs, domain, range, concavity. Like, how do we describe functions? What are the things we use when we talk about functions? That's what this chapter is about. Input, output, domain, range, concavity, increasing, decreasing. And we're going to get our feet wet actually talking about specific family of functions called quadratics. We've already talked about linear functions, and now we talk about quadratic functions, and I think you might recognize quadratic functions something like that, ax squared plus bx plus c. That's in standard form. You may see it in factored form, right? I don't know, it would look like d times x minus e times the quantity x minus f, right? Is that in factored form, some sort of factored form?
Where do you get EF from?
There's something, right? Just like where A and B from? A, B, and C, D, E, and F, those are all called parameters, right? So there's some value. They stand for a constant. We don't know what that constant is, okay? But you could imagine this, if D, E, and F all had values plugged in for it, we would call that factored form. Is that okay? Say yes.
Yes.
Okay. What can you tell me about, let's see, we can get rid of this guy for a second. Oh, I thought I got rid of him. I didn't. All right, what can you tell me about ax squared plus bx plus c? There are some things, I think, from Algebra 2 that you should be able to tell me just about this function. Is he playing Tetris? Oh, all right. Miles, something for me?
I can factor in because of plugging into your calculator.
Okay, so we can put it into our calculator. You can factor. When we factor, what's some of the reasons we would factor this?
To find the x values
that correspond to y values that are
0.
Good. All right, so you can find the zeros. As a matter of fact, Miles gets us off on a very good start. Can you tell me what x values have zeros for this function, ax squared plus bx plus c? And you're not going to be able to say like 5 or -2. Not A.
B.
Not B. Not C. No. No way. Don't you remember? This is what... No, this is what your Algebra 2 teacher, I'm sure, and probably even your Algebra 1 teacher, spent a lot of time teaching you where those zeros were. I thought you were going to do more than that. Negative B. Oh, well, why didn't you ask? I mean, all you had to do was ask us, right? That's what the quadratic formula does, right? It finds you the zeros of the function. And I need to impress this upon you. The quadratic formula is pretty amazing. There's no other formula, or I should say this, the formulas, if you have a cubic or a 4th degree or a 5th degree, are very, very cumbersome and very hard. The quadratic formula, if you give me any quadratic equation, it finds you the zeros. That's awesome. It is very cool that it does that. All right, so this is where the zeros are. So we have zeros at x equals negative b plus or minus square root of b squared minus 4ac all over 2a. Dan, you actually told me something else. All right, so it has a vertex at x equals negative b over 2a. And if you remember, look at this. There's negative b over 2a, and the zeros happen plus a little bit and minus a little bit. Wake up, Andrea. And minus a little bit. So the zeros are symmetric with respect to the vertex. So parabolas have this very nice symmetry. So if I drew you some parabola, I don't know which one, and I told you it had zeros at -1 and 5, you could go right in the middle of that, and you could say, guess what? Nope, that's not right. At x equals 2 is the vertex, because parabolas have this very nice symmetry. Did your Algebra 2 teacher prove to you the quadratic formula? Like, did they do that?
They said it works for anything.
Like completing the square? Like, did you do that? Did you do like completing the square? And then the whole reason you really did completing the square was because you can then complete the square for ax squared plus bx plus c and show that this is what solves it. Can you remind me what is isn't there the vertex when you complete the square? Don't you get it into like? Isn't there another form?
Vertex.
Yeah, what's that? Like. Great. Does that sound familiar? Is that right? Right. Yeah, so K is something. I agree.
I remember like why is it A or K times A? K is the Y.
The vertex here is H comma K.
Oh, right. And then I remember they always tried to trick us because it would be like
It is
plus
negative.
H minus K.
Oh,
Yeah.
Oh.
Is that okay?
I hate that.
I know.
Will you Okay, so it's.
What is H?
You can say no, and that's fine. If you say no, I'll be a little disappointed, but I'll be okay. It's like ninth period with a few minutes left. Would you indulge me in letting me show you a little bit of algebra?
Yes, I see you do.
All right, that's fine.
What's H?
That's fine. That's fine. I will not push it. Had it been like second period on a Tuesday, I may have pushed it. That's where the vertex is. H comma K. Okay? Say again? Yeah. All right. This function is concave down. And as a matter of fact, quadratics come in really two flavors. Concave up or concave down. And you remember you can actually tell if it's opening up or opening down by looking at what? A. No, yeah, okay.
I did last night.
But if you look at A, right, if A is positive, it opens up. If it's, no, we still have like 5 minutes. Yeah, Tom is too.
So you're becoming.
I was, okay, wait, just so we all know, I was actually talking to
Okay, I love
Tom.
how that caught on.
So, it can be concave up or concave down. Alright.
Oh my god, you have so much
It is. I forget. I don't like you all as much ninth period. No, I want to stay here.
Can we please stop this awful recording?
All right.
Yeah, really. He thinks all the time.
All right. So if we look at the slopes, bear with me. I'm waiting for something to come up, but I'm going to show you something. Sam, Elizabeth, Rafaela. The slope here, if you had to guess, positive or negative? Positive. Could we say like maybe it's around like 3, just as a ballpark? The slope here? All right. What about the slope at the very top?
0.
So just for that brief instant, the slope is 0. It's not increasing. The function isn't increasing or decreasing. As I come back down, right? So here it is. The slope here is decreasing for all of the slopes on this function, and we know when the slope's decreasing, it's concave down. So I want to reinforce that idea of decreasing slope means the function's concave down. Say again? It is frowning. It's true. Concave down is a frown, and it sort of rhymes, right? I don't have one for concave up, like a smile when you're feeling up or something.
Concave up is a cup. Because you gotta catch the one.
Ah.
Yeah, that's not bad.
I thought
All
we
right.
talked about that. Actually, that's good.
Say again? We're allowed to talk about concavity again.
No, I thought we talked about the top one.
Oh, okay. All right.
I'm gonna go home and cry.
I think I think the reality of it is